in free fall, it's very, very interesting. As you're falling, let's say you had the case of the circular orbit. You had a circular orbit, right? And let's say someone else is falling straight down, okay, and falling to the planet. And they're crossing paths. So one is going like this, and one is going down. All right? So, and let's say they're looking at each other. They see each other as they pass. What will each see? So you can have 3 observers falling into the planet. As he's falling in, he sees somebody orbiting the planet in a circular orbit, crossing his path right in front of him. You can have somebody else being shot out of a cannon coming by this way. And there's this bungee, so to speak, tunnel guy coming up and down, walking up his head right at the surface, and all 3 of them are like passing each other. They have very different velocities. One has a velocity this way, one has a velocity this way. They're moving in different directions, patterns, and so on. What do they see when they look at each other? We also know that when you're in accelerated motion, at the same acceleration as something else, neither of you will notice acceleration, right? If you're accelerating relative to something, and something else is accelerating at the same speed and so on, you're like 2 trains, 2 subways moving along parallel tracks, and you're both accelerating. You'll look in and you'll see the other people there, and they look like they're not moving. Now, of course, you'll feel inertial forces, so you'll know you're accelerating. You'll feel yourself pushed back, right? But when looking at the other person in the other train, you can't tell that you're accelerating. But he can tell he's accelerating, and you can tell you're accelerating because you're both feeling inertial forces. When you're in gravitational free fall, you're both accelerating with the same acceleration, but you don't feel inertial forces. So again, there's no way of distinguishing that from totally inertial motion. If you imagine a few particles, each one in free fall, meaning none of them are fighting gravity. One is shot out from a cannon, like this. One is orbiting the Earth, like that. Another one went straight through the Earth and is going up and down, kind of in the Earth tunnel, which maybe you've seen in some course, right? Going through the Earth in a tunnel to the other side, bounding up and down. So you have these 3 particles in different motion. None of them are fighting gravity. They're all in free fall, right? The projectile was shot. It has an acceleration of gravity, but there's no other forces acting on it. The same thing for the orbiting particle, the same thing for the tunnel particle, right? When they cross paths, this one is going up like this, right? And this one is shot up like that. At this point where they meet, what is the relationship between the accelerations that each one has?
Do they have the same accelerations?
Okay, that's right. They all have the same acceleration because the acceleration is determined solely by what? By the position that they're at. Right? The acceleration of a particle in a gravitational field is determined only by where it's at, not by what speed it's going and not which direction it's going, nothing, or its mass. If they're all crossing the same point, by definition, they all have the same acceleration towards the Earth. However, being in free fall, all have the same acceleration, just like the trains, if they all have acceleration, then 2 things happen. First of all, they don't see any acceleration of the other, but also they don't feel any inertial forces. So as far as they're concerned, all 3 are in inertial motion, or in an inertial state. Now, because they have different speeds and different directions, they will see each other moving, but at constant speed in certain directions, without acceleration. Obviously, if they separate from each other, then this one has an acceleration towards the center of the Earth, and this one has acceleration to the Earth, but that's already in different directions. At the moment that they're at the same point, their acceleration is the same in magnitude and in direction. If we catch them all if they all almost collide exactly, right, and they're small enough frame, then basically they're all in inertial motion. So what trajectories will they perceive that the other one has?
Towards them? Or towards that point?
Relative to them?
Relative to them. They're looking at it. What do they see?
Some skewed diagonal lines?
I see one guy.
Okay, so this is something to think about more.
Oh, well, the guy who's going down like this and the other guy is going from right, you'll see the guy going kind of diagonal that way.
Okay, in a straight line? Or like
I think straight line.
the guy in a cannon is going like this? Why straight line?
I don't know. So
Okay.
Well,
Anybody else?
the rate of velocities.
How long of a glimpse is this? a guy is falling through the middle of the. Are we assuming that the Earth is also transparent, or?
Well, let's say they meet at the surface of the Earth. Maybe you can give the guy a certain speed also as you throw him into the tunnel, so that he'll emerge at the same height that you threw him in,
Right.
assuming no air.
But you're
Right.
also assuming you can see each other when you're going through the Earth, right?
No. Let's say as he emerges from the Earth with the same speed that you gave him before, after a complete cycle, the other guy is orbiting and
Yeah.
cutting across him, let's say, and the other guy, the cannon, was aimed at them and coming. So they're all in air,
Mhm.
right at the surface of the Earth. 3 or 4 of them, like. So your answer was correct.
It'd be assumed they're going parallel, no perpendicular to each other.
So they're all in free fall, which means they're all moving with the same acceleration. So you can take the A out of all the equations. If you have x is equal to x0 plus v0t plus 1/2 at squared, where A is g, acceleration of gravity, we're assuming, let's say, a uniform field near the surface of the Earth, so we'll just take g in the moment.
Right.
But which is obviously not true for the guy in the tunnel, and so on. But just, let's say right here, we'll just say g, right? Y is equal to y0 plus et cetera, et cetera. You can take A out of it, because none of them feel any accelerations. They're not accelerating relative to each other. It's the same acceleration for all of them. They're all, by definition, if they're in the same place, feeling the same acceleration. What happens when you're accelerating in the same way as something else? You cannot detect the acceleration by looking at the other person who's accelerating the same way as you. Now, the person may be with a different speed, just like an inertial frame. If you're on a train or a plane, if the thing is moving with an additional speed, then you'll just see a speed add to it. If it's accelerating relative to you, then you'll notice that it's accelerating. In a free fall frame, you're all accelerating the same acceleration. You're not going to notice any difference between the two. If one of them has an additional speed beyond yours, or is moving in a different direction at a certain speed, constant speed in addition, what you'll see is simply them moving away from you or towards you or whatever at an angle at some constant speed. Correct?
Right.
So basically, you're all in an inertial frame, and you see each other moving in inertial motion. There's no difference from the case of totally inertial particles. So again, we have this amazing idea that gravity can be gauged away. If you go to the right frame, the free fall frame, you just don't need that A in the equation. There's no acceleration here. It's just cases of inertial particles moving in different directions. From a different reference frame, which is stationary with the source, right? They're all accelerating and moving and so on and so forth. But the simplest way to view it is to choose the correct coordinate system, the right axes, the right reference frame. And you do that by going in a free fall frame, and then all these spurious forces that you call gravity disappear. Okay.